All right. Well, Honors Algebra 2. 11.6 represents the end of the statistics part of this unit. The remaining sections, 11.7 up through 11.11, is going to be, we'll talk about probability. So to wrap up our statistics, we've gone through everything up through conclusion and bias. So you now have an idea of how to collect data, how to display data, how to analyze data, and how to look at the conclusions and bias of the data. Our last part is going to be about regression, so how you can build some models, being either linear, quadratic, or exponential, to model your data. So we'll look at a few different examples of this, as well as talking about what are called residuals. So let's get started. For this first example, track and field day. The table below shows data for 12 students in a stats class. Each member of the class ran a 40-yard sprint and then did a long jump with a running start. So let's make a scatter plot of the relationship between sprint time and long jump distance in seconds, and then describe the association. And there'll be kind of 4 parts when we're talking about describing the association. So when we do get there, just know that that's kind of what we're going to be looking at here. So I'm just going to write that real quick so that you can see that we're going to have 4 parts of our description. Okay, so first thing we need to do, and when we make our graph, we're gonna do that using our graphing calculator. If you wanted to graph all this by hand, it's not too bad to do, but let's just use our graphing calculator to make our life a little bit easier. So let's do this. Let's go into our stat menu, which is what we've been using before. We're gonna go ahead and press enter for edit. And I've already got these typed in to save some time. So if you need to, at this point, go ahead and pause the video. We're gonna put all of our sprint times into list number 1. And all of our long jump distance is in inches in list number 2. And again, you would probably think that sprint time is the explanatory variable anyways, and long jump distance is response, just because you think that the faster you can sprint, the further you can long jump. And so a shorter time should be a longer long jump distance, if that makes sense. Okay, so once you've got all that in, let's talk about how you're going to graph this on your graphing calculator. So rather than going to y equals, which is where you'd put a function, you're going to hit second y equals where it says stat plot above that y equals button. And we're going to go ahead and turn one of these on. It doesn't matter which one. Let's just use plot 1. So the first thing is we've got to turn it to on, and then for type, let's make sure it's as a scatter plot. And then we'll do this for X list, that's list 1. For Y list, that should be list 2. So I need to change that second 2 to get list 2. And remember, you can do that for any of your buttons that you would need is second, and then whatever number for whatever list that you're using. Let's do this. Before we graph it, let's just go to y equals, make sure we've got everything cleared out. So you notice I already have something in there. Let's clear that. And then instead of just hitting graph, probably the better thing to do is to go zoom, and then there should be an option here towards the bottom which says zoom stat. So that would be option number 9. And if you hit zoom 9, you should get a graph that looks something kind of like this. So let's go ahead and graph that. We're going to just sketch what that looks like here. I'll do that in this OneNote page. So I'm going to draw in my 2 axes and draw in my points approximately where they're at. And again, this isn't going to be perfect, but something that just pretty closely resembles what you're seeing on your own calculator screen. So something kind of like this, and again, not perfect, but matches closely enough to where you can tell that they're from the same graph and same data. Now here's the 2 other things we're missing. Remember that we really need some labels in here to make our graph look a little bit better. So our explanatory was sprint time, so I'm just going to write sprint time, and that was in terms of seconds. And then we had our long jump distance, and that was in terms of inches. Okay, now that helps, but without numbers, this data is kind of meaningless. So let's write down what our numbers should be between. And the easy way to do that is back on your graphing calculator to click on that window. That will tell you exactly where your values were. So it tells us that the x minimum was 4.83 and that the x maximum is 7.47. Now, yes, we are truncating our graph here, but when you're doing a scatter plot, it's okay to truncate. Not necessarily good to truncate on like a bar graph and stuff like that. And then for y minimum, we're at 44.77 up to 204.23. Okay, so there is our scatter plot. Next, it wants us to calculate the line of best fit using your graphing calculator, and write the equation along with the R value. Before we do that, I suppose we did need to describe the association. I told you that there were 4 parts to that. So the first thing when you're describing is the direction. And what we mean by direction, is it going in a positive direction or a negative direction? In this case, because it's going down, that's going to tell you that this is going in a negative direction. The second thing that you have to describe when you're looking at an association is the form. Does it look like it's going down in a linear form, so straight down? Does it look like it's a quadratic form? Does it look like it's an exponential form? And I would say that this one pretty clearly looks like it's in a linear form. The next thing is the strength. So you want to talk about how closely the points are to each other. And I would say in this case, while it's not super strong, and for a strong relationship, you'd almost want them to be in a straight line, I would still call this a moderate strength. It's not necessarily weak. Weak would be where you could almost barely tell which direction it's even going in. And then the last thing is any outliers, or we sometimes call them influential points. And to me, looking at this data, I don't really see any points that are kind of far away from the rest of the data. So I'm going to go ahead and say that there are none. Okay, so now we're ready to get our line of best fit and get an equation with the R value. So first thing, to get the R value, you're going to have to do a couple of things. First thing, if you have a newer calculator like the TI-84 Plus that I'm using, then you should be able to just click on the Mode button and then scroll down to where there should be an option called Stat Diagnostics. And again, that should be towards the bottom, and make sure that that's turned on. And you notice that I've already got that turned on, so I'm good to go. If you have an older graphing calculator, like a TI-83 or something like that, then you're going to find that option in the catalog. So if you hit second and then 0 for the catalog, it's going to give you an alphabetical listing. So unless you want to sit there and scroll all the way to the D's, then if you look right above the X to the -1 button, where the letter D is, if you just click on that, it'll take you straight to the first D command, and then we just have to scroll through the D's, which shouldn't take as long, for an option that'll be called Diagnostic On, and we'll press enter for that, and then you'll press enter one more time. It'll tell you done, and then that means you're good to go. Okay, so now that that's on, we should be able to get our R value without any issue. Let's go ahead and find our line of best fit. So our line of best fit, we're going to go Stat over to Calc, and then we're going to pick one of these options below 1 var and 2 var stats that say regression after them. In our case, we want to do a linear regression, so we're going to choose option 4. Later on, we might have a chance to look at quad regression or cubic or maybe even some exponential regression once we're done with linear. So let's go ahead and press enter for linear regression. It's going to ask you to make sure you're using the right list. For X list, that should be list 1, so let's change that second 1, and the Y list is already good as list 2. We're going to skip over. You shouldn't need to put anything for frequency list, and for store regression equation, we might talk about that a little bit later, but we don't need to do anything right now. And then we're going to go ahead and press calculate. If yours didn't have a menu, then you should just be able to press enter once you see linreg. If you wanted to type it in, you would just type it in as second list 1, comma, second list 2 after linreg, and then that would let you get these values as well. Okay, so here we go. It tells us that our line of best fit is going to be that y is equal to -45.74x plus 414.79. Now, a couple things to mention where I got those values. It tells us that A is -45.74. I'm just putting that into this equation for A. And then doing the same thing with B. Now, I will just say it's kind of a more common thing to do if you put this kind of symbol above the Y. We call that Y hat. And that's just any time you are using a linear regression for an equation. That's typically what you want to do. The second thing you want to do is you want to define what each of those variables represents. So Y hat represents the predicted long jump distance, whereas X represents the sprint time. And then it did also want the R value. So the R value in this case was -0.838, which would have also told you the negative tells you that this was a negative direction, and the 0.838, since that's less than 0.9, tells you that this would have been a moderate strength. So that's where you can also use the R value to check both your direction up here as well as your strength. So kind of a nice thing to have to be able to work with. Okay, so now let's interpret a couple of things. Let's interpret both the slope and y-intercept. The slope is negative 45.74. That means for each 1 second increase in sprint time, that the long jump distance decreases by 45.74 inches. So that's a pretty big jump. If you think about for every 1 second that you're dropping by that much, pretty crazy to think about how far that'll drop you off. The second thing I wanted us to interpret was the y-intercept. So that would be that a sprint time of 0 seconds, which isn't possible, so not necessarily a good way to think about this, but a sprint time of 0 seconds would result in a long jump distance of, 414.79 inches, which isn't even reasonable. That's kind of outside the scope of our data. That would be an example of what we would call extrapolation. So extrapolation would be where you're getting data that is kind of too far outside of what you would expect to get. It's unreasonable kind of answers. Okay. So in this next example that we're going to look at McDonald's beef sandwiches. I think we used this data maybe once before. If not, we'll use it now. So the first thing it asks us for is how can we determine the best regression line for a set of data? And the best thing to do for that is to look at the R-squared value. And if you notice over here on the left, we still have that up for the most recent example. R-squared was 0.702. What that R-squared value does is it tells you what the best model is for the data. And so what you actually would want to do is you would want to look at the different options. So in this case, we'll actually take some time. This will be a little bit longer day of notes, and that's okay. But we're going to do a linear regression, we're going to do a quadratic regression, and we're going to do an exponential regression, just to see which one fits the data best. So to do that, let's go in, let's edit our data. So stat, we're going to edit. Since we already have all that in list 1 and list 2, go up to those, hit clear, press enter. That'll get rid of all the data in those lists so that you can start fresh. And now we can go ahead and start to type these in. So let's do this. As far as explanatory and response, let's use the amount of fat as explanatory. So that's going to go into list 1, and then carbs will be our response. That'll go into list 2. The reason why I'm making those decisions, if you think about a sandwich, the bigger the sandwich, the bigger the bun. So the more fat for the sandwich, the bigger the bun, the more carbs they're going to be. That's kind of why I'm making that decision. All right, so let's start typing those in here, which would help if I switch to the right screen. Let's get rid of that. Let's go over here. So we're going to start by typing in 9, 12, 23. Oops, I got off a little bit. Let's try that again. 9, 12, 23. 19, 26, 42, 29, 24, and 28 for list 1. So then list 2, let's put in our carbs, 31, 33, 34, 37, 40, 40, 45, 37, and 38. And again, if I went too quick through that, feel free to pause the video, get all those in, and then we'll look at each of these once you're done. Okay, so going through and checking each of those. We're going to go back into stat, over to calc, and let's go down and choose our linear regression first. We're not going to write down the equation, we're just going to write down the R-squared value to see which one it works best for. So list 1, list 2, that all looks good. Go ahead and hit calculate. So our R-squared value in this case for linear regression was 0.55. So let's go ahead and write that in here. 0.55 was R-squared for linear. Now let's go ahead and do the same. Let's go ahead and do that for quadratic. So let's go back into stat, over to calc. We're going to choose option number 5 for quadratic regression. Still list 1, list 2. We can go ahead and hit calculate. And this time our R-squared value is 0.65. Okay, last one here for exponential regression. We're going to do the same thing. Let's go into our stat, over to calc once again, and exponential regression is going to be actually further on down the list. So you'll have to scroll past the ones that you can see, and it should be option 0 here, exponential regression. Again, list 1, list 2. And let's go ahead and hit calculate. And our R squared in this case is 0.583. Okay, so as far as which one we would say is the best one, we would say that quadratic is probably the best fit. However, just to make the rest of this example work out for us, and since I'm not going to ask you for anything besides linear regression, we're just going to stick with the linear regression equation. But if you wanted to kind of try out some of these other equations to see which one actually goes the best through all your data, that's kind of how you would do that. All right, so the next part, is the least squares regression line resistant to outliers? The answer there is no. If you have any outliers, it is going to affect things. Okay, so for part C, calculate the equation of the least squares regression line. And we've already done a few different types, linear, quadratic, exponential, to decide which one works best. We said quadratic, but for the sake of kind of the rest of this, we're going to go ahead and stick with linear. Make sure to define our variables, we will, and then sketch a scatter plot with the graph of the least squares regression line. Okay, so here's what we're going to do. Let's go back into stat. We need our equation for linear, so we're going to go back into stat, over to calc, option number 4. Now, in order to graph this on a graphing calculator, let's do one more thing. Where it says store regression equation, let's go ahead and store this into y1. So the way we'll do that is we'll hit vars, move over to yvars, we'll go ahead and hit enter for a function, and we'll choose y1. Which is the same thing if you're doing this on the home screen and yours maybe just says linreg, then all you need to do after it to get this to work the same is to type in, well, there shouldn't be a comma here, so get rid of that. But list1, comma, list2, comma, y1. And again, you'll get to y1 the same way that I just showed you. So now we should be ready to calculate this. I'm going to go ahead and hit calculate now. That'll be so we can write down our equation. So we're going to say that y hat is equal to 0.32x plus 29.62. Okay, and then also wants us to sketch this graph. I'm just going to do it on Graphing Calculator, and then if you want to sketch it on your own, you can. We should be able to use all the same stuff. If you go to your y equals, you should see that equation typed in there for you, which is kind of nice. You'll see plot 1 turned on. Let's just make sure that plot 1 is all the same data that we want. So yeah, list 1, list 2, that all looks good. And then to graph it, remember to go to zoom, choose option 9 for zoom stat. Now you've got all of your data, and you've also got a line of best fit. So I'll let you kind of sketch that on your own, so feel free to do that kind of in the space that's provided, and make sure that you're labeling your axes. So when you need the numbers, make sure you hit window to get those, but I'll just kind of leave that for you to do. Same with part D, interpreting slope and y-intercept. If you need an example of that, go back to the previous example where we did that. Remember, slope is the number in front of x, y-intercept is the constant by itself, and just give an interpretation of each of those. Let's go ahead and do this next part though, for E, which is a little bit different. It asks us to calculate and interpret the residual for the Big Mac, which had 45 grams of carbs and 29 grams of fat. So to calculate a residual, here's what you do. The residual is the difference between the observed y value and the expected y value. In other words, residual is equal to y minus y hat, which is observed minus expected. So in the case of example E, looking at these two values, 29 grams of fat would be your x value, and 45 grams of carbs is the actual y value. But what we want is we want what the equation says. We want to know what y hat is. The easiest way to do that, if you're on your calculator screen, is to hit trace, and then make sure that your trace is on your line of best fit. Right now it's on a data point, so to switch to your line of best fit, just hit the down arrow or the up arrow. And now if you move left to right, you should be on your line instead of on the points. If you're still on the points, then it's just going to go from point to point, which isn't what you want. You want to be on your line of best fit, so hit up or down to make sure you're on your line of best fit. And then you can just type in 29, and it will tell you what the prediction was at 29. So you can see the prediction there was 38.98. Okay, so our prediction was 38.98. So then to get our residual, we would take our observed, which is 45, minus expected, 38.98, which gives you a difference of 6.02. Which means, as far as interpreting it, that our line of best fit underestimated, so underestimated by 6.02 carbs. Now you might be looking at a positive 6.02 and wondering how that's an underestimate. The easiest way to illustrate that is to look at your graph. If you notice there's a point up here, that's the actual Big Mac value, was at 45. Our line of best fit had predicted it at 38.98, so we underestimated it by this difference, which we just found was a difference of 6.02. Okay, so here's where residuals are useful. I don't want to just kind of give you that. They're a way of kind of checking to see how well our line of best fit does at predicting the data. So one of the things we can use to decide how well it predicts the data is using what's called a residual plot. So a residual plot is a plot of the residuals against the explanatory variable, or the x-axis is probably the better way to think about that. And so the purpose is it's used to determine if a linear model seems appropriate for a set of data. And so how can you tell if it's appropriate? That's where you have no pattern in the residual plot. In other words, the points are roughly split 50-50 by the x-axis, their spread is consistent throughout, etc. So let's go ahead and make one for our McDonald's data. And we're going to do that on a graphing calculator because you don't really need to know how to do that by hand. Okay, so to make it on a graphing calculator, first thing you're going to want to do is you're going to want to go to y equals, and you're going to want to clear out the line that we had in there. So your line of best fit, go ahead and get rid of it. Second thing, you're going to go up into your stat plot menu, so second y equals. Go ahead and choose that plot number 1, which is turned on. We're going to leave it as a scatter plot. We're going to leave xlist as list 1. What we're going to now do is we're going to change our y list to be all of the residuals. So to do that, here's the easiest way. If you hit second and then this stat button where it says list above it, there should be an option down there towards the bottom which is called resid, which would be all of the residuals. If you don't see that as an option, you probably have not done the linear regression yet. You have to do linear regression and get your line of best fit before you can get this residuals. And then once again, anytime you want to graph, zoom, option 9, that's going to give you a residual plot. So as we're looking at this, it does look like they are somewhat evenly split out. It looks like there's only 3 of them above the y-axis, or the x-axis here, and a total of 2, 4, 6 below. That's not good. You want it to be about 50-50. The other thing is, some of these points are pretty far off of your line of best fit. I'm looking kind of at this value here and this value here. So as far as constructing, that's what it would look like if you wanted to give a sketch of that on your own paper. That would be fine. Let me go ahead and scratch this. We'll draw it a little bit better. Let's see. We've got 1, 2, 3, 4, 5. One up here is 6, 7, 8, and then 9. So what we would say is no, linear model is not appropriate. And again, the reason for that is you've got some values in here. You've got too many that are below, not enough that are above. You've also got some points that are pretty far off of this x-axis, which is not good. What you really want to see when you do a residual plot is about the same number above as below, and you want them to be about the same distance from that line of best fit. That's what we mean by the spread is constant. So this is more ideally what you're looking for. I would say the one that we had, linear model, would probably not be appropriate, which should also kind of make sense because earlier on we said that a linear model was not appropriate, that quadratic would probably be better. So all right, that's what I've got for you guys. That is regression, just kind of a crash course in it. Obviously, if you are interested in that kind of stuff, we do cover it in both stats and AP stats. So if you're looking for a little bit more in terms of that, take some of those classes later on. That's all I've got for you today. Have a good one, and I'll talk to you next time.